Okay, so lecture number 17, we're going to continue on with reinforcement learning topics. So today we're going to talk a little bit more about exploitation versus exploration, and we'll talk about sort of the simplest form of actual numerical algorithmic reinforcement learning, which is a simple Bandit algorithm, and how that helps us to solve the exploration versus exploitation. And by solve, I don't mean it's the only possible solution, but it's one of the simpler solutions that we could implement. So just as a little bit of a recap, we talked last time about how one of the main challenges in reinforcement learning is the trade-off between exploitation and exploration. And so in order to obtain a lot of reward, we have to take the actions that we know give us high values. But in order to know which actions have high values, we have to actually try those actions first, right? So that's the whole exploitation versus exploration. So in order to learn which actions produce those rewards, we must try them out first. And so you have to exploit the knowledge you have, but you have to explore in order to gain more knowledge. And that balance can be a little bit tricky. And talked a little bit last time about how this is also one of the main challenges in real life where, maybe I've been to 10 different restaurants in St. John's. Do I go to one of the ones that I've already been to because I know it's kind of good, or do I try my 11th restaurant? Okay, so before I get started with this, just a quick note about what learning is. There are a lot of different definitions of learning, but I would say that learning is the process of either gaining new knowledge or modifying existing knowledge. And that's what we're going to be doing during this lecture, is sort of the mathematics behind what is my belief of the value of this thing, how do I update that, and how do I make decisions based on that. So we've learned something if we have information that we didn't have before, right? So if I step outside and, I don't know, there's a car parked outside or something like that, then I didn't know there was a car parked there, and now I have that knowledge, etc. But the cool thing about learning is that even if you are given the exact same results, you're still learning. And what you're learning is that you're learning to trust those results with more certainty, okay? So our estimate is going to have less variance. So even if, I got some reward from some action and the reward was 100, if I do that 10 more times, and each time I do it, I keep getting 100, I'm still learning, right? Because now I know that, hey, I got 100 10 times in a row, and I'm much more certain about that 100 than I would be if I had only gotten it once. And we'll see an illustrated example of why that is a little bit later. So exploitation is exploiting our current knowledge, and essentially what this means from a reinforcement learning context is that we're going to choose these high-valued actions for which we already know the value. And so what this is it's kind of a low risk, but potentially low reward as well. So we know what we're going to get, and so we choose the thing that we know what we're going to get, but there could be something out there that's better. And so always choosing actions that we are familiar with, it gives us not much new information. So yes, it might give us the same results like I was just talking about, but typically you learn more as you do different things that you haven't done before. And that's going to come through exploration. And so exploration is trying actions that we haven't tried before, or trying actions that we have tried far fewer times than other actions than we may have tried. So it doesn't necessarily mean that we're trying something for the very first time, but we're just trying to reduce the variance of our statistics that we've gathered when it comes to things like the rewards that we've obtained. And so this helps us learn the action values a little bit better. And it's possible that the new actions that we try are going to have higher rewards than previously selected actions. And so that would be the best case when we learn to do something better. But of course, it's always the case that the new thing we try could be worse, right? And so if it's worse, it doesn't mean that that's wasted information, because now we know that the thing we had been trying with more certainty is actually pretty good. And so whether or not we try something new and get something good or something bad, it's still learning, and it's still all very useful information. So once we've explored sufficiently, we can exploit the best actions, and then we can sort of have some sort of measure of certainty of how much we know, right? So if we've tried each action just once versus we've tried each action 1,000,000 times, we're going to be more certain of the values of those actions. So one of the examples and where this term bandit algorithm comes from is from a slot machine. Who here has played a slot machine before, either real or virtual? A few people? So these slot machines, essentially you walk into a casino or some online game. I'm not promoting gambling at all. These things are designed to take your money, hence the term bandit. And these slot machines, at least in the past, they had a big arm on them, because before there were computers, these things still existed, and what you do is you would pull this with enough force that the actual dials inside would spin, and then based on the amount of force, they'll stop, right? So if anyone's seen The Price is Right, where you spin the big wheel, sort of the same thing was happening in these machines. So, so these were called the one-armed bandit, because they had one big arm and they would steal your money. So that's one-armed bandit. And here what we're going to do is we're going to treat these problems as an n-armed bandit, meaning that we're going to have n different slot machines. And so that's where this name comes from. So we're going to repeatedly make a choice among n different actions. And after each action, you're going to receive a reward from what I'm calling a stationary probability distribution, depending on the action. And what stationary here means is that the distribution, the statistical distribution from which the machine will give you a reward. So for example, it might be 40% of the time you win and 60% of the time you lose. And so if that 40 and that 60 stay the same every single time, that's called a stationary distribution. And if that 40 and 60 could change, right? So for example, maybe some online truly evil game might have you win a bunch right away and then turn it down so you lose more over time. That would be called a non-stationary distribution. And so the objective here is to maximize your expected total reward over a number of action selections. So for example, typically in the real world, what will happen is, okay, maybe I have 4 different slot machines and I have $100. Or someone has said, I can make 100 total guesses. And I'm trying to maximize my reward within that. Now, the actual problems we're going to be solving with these bandit problems don't have to be related to slot machines, right? It could be pathfinding, it could be some action that a robot is doing, etc. But the slot machine is kind of a good analogy because it could just give us some randomized reward that we can use for learning purposes. So this is called the multi-armed bandit problem, which I've already stated. So this is an analogy to slot machines that are called one-armed bandits. And so you're going to have some limited amount of money or limited amount of time or some resource that you're spending in order to take these actions, and then you're going to try and win as much as possible over some amount of time. But how do we select which levers to pull, right? So over here, we've got the same thing. So you can see sort of how an example like this is related to the n-armed bandit problem, because I've got n of these doors. Behind each door, one might lead to $1 million, one might lead to, I don't know, someone screaming at us, another might just be a room full of fire. You never know, right? But when it comes to other problems like pathfinding, it may not be obvious at first how this is related to the n-armed bandit problem, but essentially, when you go up, down, left, or right, you're going to get some reward from doing that. One of those directions is going to be better than the others, and you'll want to go in that direction. So the two problems are quite related. So if we maintain an estimate of action values, at any time, one of them is going to be the highest, right? Or we may have multiple highest, it might be a tie, but at some point I've got some values, I've got some guess, okay, this slot machine is giving me 40 cents every time I pull it, this slot machine is giving me $2, I'm losing $100 with this one, so I've got some guesses somehow over some number of actions at how good these slot machines are. And so at one point, one of them, it just has the maximum value, right? You have any data set, one of the things has to be the maximum. And so that one that currently holds the maximum value, which is an estimate, of course, we're going to call that the greedy action. Why is it called the greedy action? because if I just take the thing that has the highest current value, I'm just being greedy. I want the best thing that I currently know. So exploitation would be choosing the greedy action. That's exploiting the knowledge that I currently have. And it's going to maximize single action returns. So if I said to you at any given time throughout this process, just maximize the reward you will get on the next action, then you're going to take the one that you currently believe is the highest, right? It's not a trick, it's not complex math. You're just gonna, okay, I think that one is gonna give me the best, therefore I do that one. Exploration, on the other hand, would be choosing a non-greedy action in order to improve your action value estimates, right? So this is required for future reward maximization. Because if we just, if we just pulled one and say, well, I got $1, okay, I'll just keep pulling that one. I keep getting $1. But how do I know that the other ones aren't better, right? I've got to be able to try those things. And so how do we balance that? Well, that's going to be sort of the point of the rest of this lecture, and actually the rest of reinforcement learning, in fact, is algorithms on how we do that. So there's two main concepts when it comes to actually, now we're going to start to implement some algorithms to actually store these values and choose actions. So the first most important concept, or of these two concepts, is how to store and update the value estimates as we learn over time from new information. So this is literally, as I pull a slot machine, I get a reward. How do I keep track of that information, right? How do I go from what I thought it was before, then given a new reward, how do I update that, right? That's the first thing. And then the second thing is, once I have some guesses of the values, how do I choose which action to do next, right? So one is this storing an update of these estimates, and the second one is using those estimates to select an action to do. All right. And so one way to do this is called an action value method. Again, not very cleverly named, but it does its job. So how do we store the current value estimates? Well, the nomenclature that we use in reinforcement learning and in the textbook is QT of A, okay? And remember when I said last time that I had emailed Rich Sutton about why G was used for return? I actually watched last year's lecture for this one, and it wasn't G, it was Q that I emailed him about. And so I don't know why G is the return, but I do know that Rich Sutton doesn't know why Q was used. It was just used in some PhD thesis, and he thinks it was just arbitrary. And sometimes when you come up with a new algorithm or method or paper, you just have to look back through previous papers and pick numbers that hadn't been used before, right? Like the C programming language is called C because there was an A and then there was a B. That's why it's called C. And so anyway, so we're using Q, and our value estimates are going to change over time, right? So if I pulled this slot machine and I got $5, and then the next time I got $10, then my estimate is going to change. So we denote the time step of our estimate by this T. So QT of A is our estimate of the true value after some amount of time steps T. And so this true value here, Q star of A, would be like if we knew the source code of the slot machine and we saw in the code, okay, take a random number between minus infinity and plus infinity, like whatever that value would actually be. So Q star of A is the actual value of action A, where actual value is going to be the mean reward, or the average over time, because these are often taken from probability distributions. They're not just, here's a single value all the time. And this is as t goes to infinity, right? Because the more samples that we get, the more sure we are that this is getting closer and closer to the actual average. And that's basically one big lesson of statistics, is if you have some distribution and you keep taking samples, as your number of samples approaches infinity, then your estimate of the average will approach the true average. The more times you do something, the more sure you are that your value approaches the true average. So how do we actually implement this? Well, let's take that example of the n-armed bandit problem. And so Q of A is going to be your estimate of bandit A's reward. Okay? So if you choose a bandit, that is one action. So I have Q of A. If I pull it, I get 100. Maybe Q of A is 100 now. Maybe it's some other formula. And let's just look at the easiest possible way to do this. And so Q could just be an array of size n for n different bandits. So if I have 4 bandits, then there's 2 things. One is how do we store it? The other is what is my initial guess at everything, right? So let's just say that my initial guess at the value of everything, that's going to be Q0. T is 0, meaning that this is the initial values. I have not tried any actions yet, okay? So if you haven't tried any actions yet, depending on the algorithm, some of them will say, just put in zeros. Some of them will say, well, don't put in zeros, actually just try each action once, and then we'll start the algorithm, okay? But for here, we're just saying, all right, let's just say that all of our values are going to be zeros. And if we end up doing something like computing the average, then starting with zeros is going to be a good thing. However, as we'll see a little bit later, starting with zeros could also be a really bad thing. And we'll see what that does. And then after some number of time steps, so let's say t could be 100, so I've pulled 100 different levers, now my values are going to look like different numbers, right? They could still all be 0, but probably I'm going to have some different values here. And just keep in mind that Q of t means t total actions. It doesn't mean that each of these has been tried 100 times. Like for example, this could be 10, 10, 60, 20. Okay, so it doesn't mean that they've all been tried 60 times or 100 times. It just means that I've tried a total of 100 things. So let's look at a nicely illustrated example. So here's the example here. If you're watching on the video and my face is like up here in the top right corner, that's just it's just another slot machine labeled 4. So there's 4 total slot machines. There's no information that's important up here. So I've got my bandits, 1, 2, 3, and 4. These are my actions. Okay, so this is A1, A2, A3, A4. I'll come back to the distribution in a second. Here, what I'm going to do is just keep a record of all the rewards that I've gotten from each bandit. So if I've pulled this one 3 times, I'm going to have 3 numbers down here. Okay, and then this value, Q of t, this is going to be Q of 1, Q of 2, Q of 3, Q of 4. That's just, after I've done some number of actions, that's the value estimate that I have for that particular bandit. Okay, so what is the distribution? Well, that's the question, right? If we knew the distribution, we wouldn't have to take samples. If we had the source code of the slot machine, I would know which one was best, because I would just do some statistical analysis on that. So what we're trying to do is come up with a single number that represents the value of sort of the average of that distribution. So for example, here are the distributions I'm going to use, and they're wildly different. So this first one, every time I pull it, it's just going to give me always 5. So every time I'm just going to get a 5. This one is going to give me negative 20 or 20, nothing in between. This one is going to give me a random value between 0 and 10. Let's just pretend that they're all integers. And this one is going to give me a random value between negative 10 and 10. And now, hand up if you can tell me which one you would pull. There's no wrong answer yet. There might be a wrong answer after we do a little bit of math. Yep. Yeah, so why would you pull the always 5 bandit? Okay, so you're always guaranteed to get 5. That's not a bad reasoning. Yep.
Number 3, since there's no negative, you're not losing anything, and there is like a higher percentage to get above 5 as well. Okay,
so here you're saying that you're always going to get something positive, and there's the chance that we could get more, right? Anyone else? Would anyone else choose 2 or 4? Hopefully not. Okay, so what you've all seen here, like you're all doing this analysis, which one has the highest true average here? So if we could pull each one 1,000,000 times, what would it give us? So if we look, always 5, well, the average of that is going to be 5, right? Pretty obviously. This one, negative 20 or 20, what's the average of that? 0. What's the average of this one? It's going to be 5 again, right? Because right in the middle, it's going to be 5. So these two have the same. Over here, we've got between negative 10 and 10, and the average of that one is also going to be 0. So we've got 2 that have an average of 5, but give us that in a slightly different way, right? And then we've got 2 that give us an average of 0, but again, very different ways to get to that average. So the reason I did this is because I just wanted to let you know that the average can sometimes be a little deceptive, right? Even if we've pulled these a million times and we're very certain of these averages, the distributions that those values come from can be wildly different, right? So the average doesn't tell the whole story ever. But still, if I'm talking about doing this over and over and over, it really is just the average that I care about. If I only had like one pull of each, then I might, choose something different based on that. But over time, the averages are what we really care about. So down here, how do I choose my initial Q values? Well, what we're going to do for now is I'm just going to say that these are all 0. Okay? And so Q0 of 1, Q0 of 2, Q0 of 3, Q0 of 4. That means the initial values for all of those. And so after I've done one action, those things on the bottom are Q1 of 1, Q1 of 2. So Q3 of 2 doesn't mean the third time I've taken action 2, it means the third total action. Okay? Alrighty. So let's try this now, but the thing I haven't done yet is tell you how I'm going to update my estimates as new values come in. Okay? The two ways that we're going to do that today, one is called the sample average estimation, and that's as easy as you think it is. I just look at all the values that I've gotten, all the rewards that I've gotten, and I take the average of those. The other is called an incremental update estimation, and I'll get to that when we after we do the average one. So the QT of A sample average estimation couldn't be easier. A natural way of calculating QT of A is to average the rewards that we've received so far after all the plays that we've done. And so if at play T, so this is time step T, action A has been chosen KA times, yielding rewards R1, R2, up to RK, then our estimate is just the sum of all the rewards divided by the number of times. That's just the average formula. I'm sure you all know that one. So if KA is 0, then we do have to pick something. We can't just divide by 0, right? And so we're going to define it as some default, and for now, let's just take that as 0. So as KA gets very large, QT of A is going to converge to the actual average. And that just means, like in plain old English, as we try everything more and more times, our average estimate is becoming more accurate. That's it. And so the average of the samples is the sample average method. Very, very cleverly named. Okay, so let's try here. Let's start doing this. So I'm going to pull, the way I'm going to choose my actions, we're not getting into that part yet. So what I'm going to do is I'm just going to go left to right and pull each lever twice. Okay, so I'm going to pull each one, and I'm going to go back and pull each one again. So of course, when I pull always 5, I get a 5. And my Q0 now goes to Q1, right? And the value down here is going to be the average of everything here. And because I have only a 5 there, then the average of 5 is 5. Now let's pull the second one, and I got unlucky this time, so I get the minus 20. The average of minus 20 is just minus 20. So Q2 of this, even though we've only pulled it once, this means that after 2 total actions, my estimate of this is minus 20. Now I keep going. Okay, I get a little bit lucky here on the random 0 to 10, and I get a 4. Therefore, my average is 4. And over here, I got super lucky, and I got an 8 between negative 10 and 10, and so my average over there is 8. Now I'm going to start back at the beginning and keep going. So obviously, I get another 5, so my average there doesn't change. Now I got the 20, right? So my average here is 0. I got a 0 on the third one, so my average now is 2. And over here, I got a minus 2, and so my average now between 8 and minus 2 is 3. Okay, so 6 divided by 2. You can all do that, I'm sure. If I gave you this slide on an exam, just a picture, right, and all the different rewards, you would be able to calculate the average, no problem. It really is that easy. Like, averages are very powerful. Okay, so that's the average. Now let's try the incremental update and talk about why sometimes we may not want to use the average. Okay, here's a bit of a spoiler. If we have a stationary distribution, meaning that those distributions will never change, and we are somehow sure of that, then the average is what you want to use. Nothing can do better than the average in that case. Okay? But what can happen is, let's say this always 5. Let's say I've pulled that 1,000,000 times and I've gotten 1,000,000 5s, right? And then something happens where that distribution changes now to always 1,000, for example. So if I've gotten 1,000,000 pulls and my average is 5, and then I get 1,000, what is my average now? It's still 5, right? It's like 5.00001 or something like that. But then if it keeps being 1,000, it's going to be hundreds of thousands of pulls before my average really starts deviating from 5. And so it would be nice if there was a way that we could sort of trust newer values more than we trust older values. This is sort of how it works in real life as well. Like we have this recency bias where things that have happened more recently we trust more readily than things that have happened in the past. So, but just to let you know, if you're 100% certain that you have a stationary distribution that won't change from 5 to 1,000, then the average is just fine. That's easy to do. However, there is also something bad about the average, and I'll talk about that in a second. Okay, so just recall that the average update formula is taking all the rewards, summing it up, and then dividing it by the number of the rewards. What is numerically or computationally a little bit bad about this? What could be a little bit bad? Think about if, okay, maybe at the beginning versus time step 1,000,000. What's going to be different? You have your hand? Yeah. Exactly, right? So the answer was you've got to store all those rewards and you've got to add them all up and then divide them, right? And so what you have is, on your first pull, your calculation is instantaneous, but then on your billionth pull, well, now you've got to iterate over gigabytes of memory and all this kind of stuff. So let's try first to fix the average formula so that we don't have to do this. So needing to store all the rewards we've ever gotten is pretty bad, especially when you're doing reinforcement learning in a simulation and you've got tens of millions or even billions of time steps. So the memory and computational requirements grow over time with this naive formula. So let's first derive an incremental formula for the average so that memory is no longer an issue. So what we have right now is that the new average with the new sample is a function of the history of all the samples we've ever done. But what we want to have is that the new average is just a function of the old average and the new sample. So we only ever have to store those two values, which would be pretty good. So, okay. Be careful, I'm about to show some math. I know that math is like, everyone's allergic to math, but this is actually a good example of that. And I know that the font size is a little bit small, but hopefully you can see it. So, what we have is Q sub k. Okay, so Q sub k, that is the incremental, or sorry, that's the average for after k time steps. So that's just reward 1 plus reward 2 all the way up to reward k divided by k. So k is the number of time steps here. And if we put that into our nice summation, then this is a summation from I equals 1 to k of Ri divided by k. Okay, so we've just put it into summation formula because that'll make things a little bit nicer for us. Now what we're trying to do is we're trying to get a formula for qk plus 1 in terms of qk rather than in terms of all of these different values. So if I take this, the sum of I equals 1 to k, and I just plug in k plus 1, then I'll get the summation formula for qk plus 1. That's what we currently have, because qk plus 1, that's the next time step, so that's the new average. That's the thing that I want. But what I want to get away from is having to do this summation, right? Because that could be a billion different things that I have to store. Okay, so let's do a little bit of math. What I'm going to do is I'm going to take out the k plus 1th, is it k plus 1th or k plus 1st? I don't know. We're going to take out the reward k plus 1 from this formula, just to make things a little bit easier for us in the future. And what that does is now we have the summation from I equal 1 to k of Ri, which is looking like what we had up here, plus Rk plus 1. Next, what I'm going to do is take this factor k outside, because if we look, this formula here, the summation of I equals 1 to k of Ri, that's equal to this. But this, because this is divided by k, and that's equal to qk, then this is actually equal to k times qk. Okay? I know I'm saying the letter k a lot. But this term here, because qk is equal to all of this, including the division, then this part is equal to k times qk. So this is good. Good, very good starting place. Now, what I'm going to do is, because I've got a k outside here, I'm going to do that little mathematical trick where I add something and subtract itself. So I'm net adding 0, but it'll make things mathematically a little bit nicer. So I've got, and I've also put this part at the beginning. So now I've got kqk plus qk minus qk. All right? And then what I'm going to do is I'm going to factor out, because I've got k qk's here and 1 qk here. I'm going to factor that out. And now what I have is I have this formula. I'm going to take that outside. Okay? So I've got qk plus 1 divided by k plus 1 times rk plus 1 minus qk. So before, where I had to store all of my rewards, now the new average is equal to the old average plus 1 over the number of samples times the new reward minus the old average. Okay, so let's just have a look at that in a little bit more detail. So qk is the average of the first k rewards. qk plus 1 was equal to that, which we derived this from. And so now what we have is what we wanted. We have that the new estimate, which is qk plus 1, is equal to the old estimate, which is qk, plus some step size. And what this step size is how much do we pull our belief toward the new estimate. Okay, and I'll have an illustrated example of that in a little bit. So 1 over k plus 1, that's the step size if we're doing the average. Rk plus 1, that's just the new sample or the new reward, minus qk, which was our old estimate. So what we do is we have our current estimate or our old estimate, we get a new reward, and then we take that new reward and we go somewhere between our old estimate and the new reward. That makes sense, right? If, let's say, our old value was 0 and our new value was 100, then our new estimate should probably be between 0 and 100, right? You wouldn't want it to go into the negatives for some random reason. And so this new sample in reinforcement learning and statistics, that's called the target value. So the target, because that's the target that we're trying to move closer toward with our new estimate. Okay, so just keep in mind that this is the incremental update formula if you want to take the average of k samples. All right, but again, we saw that the average is really good in the case of stationary distributions. How might we do this if we have non-stationary distributions? So what if these distributions change dramatically, right? So I said this a bit before, but if the distributions remain the same, the problem is called stationary. And if the distributions are allowed to change over time, it's called non-stationary. So imagine having an average of 1 for 1,000,000 time steps, then we change it to 100. It will take a long, long time for that average to change. So for non-stationary problems, we're going to move away from the average, and we're going to say, like, okay, so averaging works fine for stationary problems, but not if it changes. So we want to weight recent rewards more than old ones in the case of value changes. So we're going to use a constant step size parameter. And that constant step size is going to be called alpha, and that's going to be between 0 and 1. Okay? So here is our new formula. Our new estimate is going to be our old estimate plus some step size between 0 and 1 that we're going to be adding this, and the thing that we're multiplying this by is the difference between the new sample and the old estimate. And I'll have an illustrated example of this, hopefully. So, not hopefully, but hopefully it makes it easier. Okay, so the new estimate is going to be pulled toward rk plus 1 by this step size of alpha. And so let's just look at some numerical examples. If my old estimate was 50, and my alpha is 1, and my new estimate is 100, Okay, so how does that work out? So here's where that works out. So it's 50, because that was my old estimate, plus alpha times the new thing minus the old thing. So the new thing minus the old thing is 50. The difference between them was 50. If alpha is 1, it means go all the way of this 50. Okay? So my new estimate is 100. So if alpha was 0.5, for example, then instead of going the whole 50 from 50 to 100, I would divide that by 2. So I'd only go halfway between 50 and 100, and I would land at 75. Okay? So if we look at this on a little graph, if QK is 50 and my next reward is 100, then this is what alpha is doing. If alpha is 1, then I will trust all the way at QK plus 1, right? Because 1 means completely trust the new sample. If alpha was 0.5, then I would go half of the way, and then my new value would be at 75. So this step size essentially says, how far do I step between the old estimate of 50 and the new value of 100, okay? Now, typically what you'll see in practice is you want to prevent these really large swings in your value estimate. Like you wouldn't want it to be 1,000 on one time step and then like minus 1,000,000 on the next time step. So typically, this alpha, when it comes to machine learning, this is typically called the learning rate. And the learning rate is like, how fast do I want to learn that this is the new value? And typically these learning rates are going to be, say, under 0.1. So 0.1 or under, so that yes, learning takes a little while, but the good thing as well is that you'll never get a value that will dramatically change your belief, because you don't want it to swing very, very wildly. So now let's take this example of a step size of alpha equal to 100 or equal to 0.5, and let's apply it to the very same numbers that we did to the average, and then we'll see how these things differ. Okay, so my Q0s, like I said, I could have chosen anything, but I just chose 0. And now let's start getting those same values. So I got a 5. My alpha value is 0. Therefore, my alpha value is 0.5. Therefore, whatever I get here, every single time, the way I update it, if we want to do the math in our head, is I'm going to go halfway between whatever this is and whatever that last value was. So halfway between 0 and 5, it's 2.5, right? Now, it may seem like I'm taking the average of two things, but it's not that, right? I'm going halfway between this and another one. Okay, let's see, minus 20 or 20, I get the minus 20. I go halfway between 0 and minus 20, so now I have minus 10, okay? The next one, I get the 4, I go halfway between 0 and 4, so that's 2. I got my 8, now I go halfway between 0 and 8, and this is 4. I get my next 5, so I go halfway between 2.5 and 5, which is 3.75. Now I get my 20, and oh, this is interesting now, because this is where I finally start to see the effects of this fixed size alpha and how it trusts more recent values more than old values, right? Because minus 20 and 20, the average of that is 0. But I'm above 0 because I trust the 20 a bit more than I trusted the negative 20. But if the values were opposite, so if I'd gotten the 20 first and then the negative 20, now I would have had negative 5 instead of 5, okay? So this does take time into account now, where I'm trusting more recent values more. Okay, now I get a 0 here, halfway between 2 and 0 is 1. And now I get my negative 2, halfway between 4 and negative 2 is 1. So here are my new values, and they can be dramatically different than just the average. But the hope over time is that as I get many, many more of these samples, I am going to get closer and closer to that average. But if you'd been paying attention in calculus class, I'm sure you've all seen this question before, right? So if I keep going half the way towards something, will I ever reach it? Right? So here, something we can say is that even though I'm always getting 5, and my value is getting closer to 5, using this fixed size alpha update, I will never actually get to the true average. I'll get really, really close, but I will never get actually to the actual average. That's one of the downsides. Now, it could be the case that if I was going, like, let's say the average was 0, and my last value was 5, and then there's a new -5, it could land on 0. So if I'm oscillating over this average, yes, it could. But for things like this, where you always have the right value, you'll never get to the right value. Okay, so that's what we have now, and this is what we had before. And you can see, just based on one of the infinite number of ways that I could possibly keep track of these values, I am having different values down here, which could impact our action selection if we think about it that way. So I'll just go ahead and say I'm probably going to give this on the final, right? The final exam is going to focus way more on the second half of the course, probably like 80% of it. And this is a great example. And yeah, you can do this calculation now, I think. All right. So that's how I update my values. But now the question is, which action do I choose? I don't want to always just go left to right and do each action the same amount of times. So let's have a look. The first one, it's called greedy action selection. The simplest possible way to choose an action is to just look at all my values and choose the one that's highest. That's it. You couldn't get simpler than that. And so on play t, time step t, choose A is the greedy action A star. Now this is not the A star algorithm. It's just the best action at any given time, right? That's what A star means. So QT of A star means that that's the maximum action for QT of A. So you look over all of the A's, you find the maximum QT of A for all those A's, and that's QT of A star. So this method always exploits. It always exploits current knowledge in order to maximize immediate rewards. And no sampling or exploration is done to determine values of another action to see if they may be better. Now, why is this bad? Well, look at this. If we happen to try the first one first, so let's say all of our value estimates were 0 initially. Now we believe that this value is 5. Well, we never pull anything else. We never try anything. If all we do is maximize, the first value that we got that was greater than 0 is the thing we're always going to pull forever. That's it. And so we never explore. So that's really bad because the second one could be always a million, right? So sometimes if you're doing something like this and for some reason you just absolutely have to do greedy selection only, it may actually pay off to set the initial value to something really high, right? Because if I set all the initial values to 1,000,000, for example, and then this gives me a 5, that brings my average way down, so now I'll try the other ones, okay? But that doesn't mean that you should always do that. This is just one example where it's the worst possible example for greedy. We try one thing and we never do anything else. So what's the way we can fix this? Well, the simplest thing we could do is this thing called Epsilon greedy. And so to add exploration, just choose a random action with probability epsilon, right? So maybe 50% of the time I choose the greedy thing, 50% of the time I choose a random action. That's a way that I could implement exploration, right? And trust me, this works. It works really well in practice to do something like this. In the limit, meaning that as t goes to infinity, each action will be sampled an infinite amount of times, right? Even if you're just saying, okay, I have a 1% chance of choosing a random action, if I do things an infinite amount of times, then I've still chosen everything infinitely many times. So as Ka, meaning the number of times we've chosen the action, goes to infinity, Qt is going to converge to Q star of A. So even no matter what the epsilon is, if epsilon values are lower, it might take a longer amount of time, but we are guaranteed that this will eventually converge to the right answer. So in theory, this may work, but in practice, it may take a long time to converge if you just have a fixed value of epsilon. Okay, so that means if I have a value of epsilon, I choose a random action with probability epsilon, and I'm going to choose the greedy action with probability 1 minus epsilon. So question for you, hand up, hopefully someone different. If I have let's say epsilon is equal to 0.1. Okay, so that means I'm going to choose a random action 10% of the time. What is the probability that on any given selection I'm going to choose the greedy action? Sorry?
7.9.
Why did you say that?
7 of it.
That's okay. So there's 4 actions. I'm going to choose a random action 10% of the time. What's the percentage of the time that I choose the greedy action? What was that? 0.5. That's almost correct. Your intuition is there, right? So if I'm choosing a random action 10% of the time, it means 100 minus 10% of the time, I'm choosing the greedy action, right? So in that case, yes, 90% of the time. The one thing that's a little bit tricky to understand is that I also could choose the greedy action randomly. So I've got to increase it a little bit, right? So here, if I've got 10% randomness, then I have 10 divided by 4, which is 2.5% chance to choose the greedy action via randomness. So I actually have a 92.5% chance to choose the greedy action. Okay? So I wasn't trying to trick you there. Your intuition was completely right. That's just the little tricky extra step for the exam, right? If I ask you a question like that. Okay, so again, just to drive it home, epsilon means with that probability, I choose a random action, but with the other probability, 1 minus that, I choose the greedy action. All right, here's a graph that's a little bit hard to, just for the colorblind people. So green is here on top, red's in the middle, blue's on the bottom. And over here, this says average reward, and this is the number of time steps. So this is a graph meant to show, this graph is straight from the book. It may not be the best example to show, but it was there and it's in the book. But what this shows is the blue graph is an epsilon equal to 0. And this is showing that my average reward over time is not going up if I don't explore, essentially. Whatever I happen to get on that first pull, I may just keep pulling because that's the greedy action if I'm doing no exploration. So if epsilon is 0, it's never triggering, and so I'm never getting a random action. This green one here is epsilon of 0.1. So that means 10% of the time I'm doing a random action. So I am sampling other things, so then I can know if there are other things that are good, right? So my average reward over time is going up if I explore. And you can see here it goes up pretty quick, but it plateaus at a specific value, right? The reason that epsilon greedy will always plateau is because 10% of the time you're choosing a random action. So even if you have figured out what the best action is, you're never doing it all the time, right? You're always not doing that thing 10% of the time. Now, here, the red one is going up very slowly, and it's impossible to see here, but this is epsilon equal to 0.01. So this is 1% exploration. And what this means is it's going to learn slower because it's trying different things less often, but once it has gone for a number of time steps, and once it has learned as much as the 0.1 10% exploration, so once they have the same amount of information, one of them is exploring 10% of the time, and the other one is only exploring 1% of the time. And so the lower epsilon value means it's going to learn slower, but once it does learn, it's going to be choosing random things less often. Therefore, it's going to give more average reward. So if this graph extended, this is why I should have replaced this graph, but it will eventually go higher than the green one. Okay? So lower epsilon means slower. You're choosing random actions less often, so you're learning about their values a little bit slower, but in the end, you will choose random actions less, so it's actually better later on to have a lower epsilon, right? And there are schemes out there for epsilon greedy where it'll say something like, okay, for the first however many time steps, I choose 20% random, then 10% random, then 1% random. So the epsilon will go down over time, for example, because you want to do most of your exploring at first rather than later. Okay, in this graph, this is the percentage of the time that you're choosing the optimal action. So instead of just the average value you get over time, this is the number of times that you're actually choosing the actual best thing. And so we can see here the same sort of thing. So the red line, which is the lower 0.1 epsilon, is going to be growing slower, but it will eventually overtake. Why? Because this one, even though it learns a little bit faster, let's say there were 10 different actions, still 1 out of every 10 times, it's going to be choosing the wrong thing, right? Or 1 out of every 9 times, I guess, on average. But this one will be only choosing the wrong thing 1 out of every 100 times, eventually. So this is the relationship that I'm trying to drive into your heads here, is that high epsilon is faster learning, but later on, you'll be choosing the wrong thing more often. Lower epsilon is slower exploration, possibly slower learning, but you'll be choosing the right thing more often. Okay, so if we want to implement a bandit algorithm, what we have to do is we're going to choose our value update method. So for example, are we going to do the average? Are we going to do the incremental version? Second, we're going to choose an action selection method. Let's just say we're going to do epsilon greedy because we saw how greedy is not the best. And then you're going to repeat for some number of time steps or until your Amazon credits run out or until your assignment is due or whatever. You first choose an action to perform. Then you get the reward value from the bandit, and then you update your value for that action. Then it all repeats again. Based on your new values, you choose an action, you get the reward, update your values. And this just repeats and repeats and repeats. And over time, you're choosing good actions more often, your average reward is going up. So let's have a look at some pseudocode. This is going to be the incremental average formula with epsilon greedy action selection. So here we've chosen incremental average, and here we've chosen epsilon greedy. Okay, so this is the function bandit algorithm, and it's just going to take in the bandits. So the bandits could be however you want. Maybe it's some object containing your slot machines, or it's the pathfinding algorithm, or whatever, but we just take in some bandits. And so our Q values initially, our Q of 0, is going to be just a bunch of zeros. So we're setting everything to 0, and the number of those is going to be the size of the bandits. So if we have 4 bandits, then this is going to be Q, is going to have 4 elements, and they're all going to be 0. Also, in order to calculate the average, we do need to keep track of how many times each thing has been done, because that's our alpha, or our incremental step size update requires that. So this is also an array of zeros equal to the bandit size. And that starts at 0 because we haven't tried anything yet. So each of these, if I pull action number 3, then I'm going to increment 3 by 1 to indicate that I've done that. Then, while true, of course, this isn't a true infinite loop, but you'd exit at some point. I'm going to take note of which action I should do, but I need an if statement. So if rand, so let's just pretend that rand is a function that returns me a random number between 0 and 1. So a random real number between 0 and 1. So if epsilon is 0.1, that means I want to select a random action 10% of the time. So what this does is if this is truly a uniform distribution random number between 0 and 1, then that will produce a number less than 0.1 approximately 10% of the time. So this is how we will do that. So if rand is less than epsilon, then my action is going to be choose a random action. Otherwise, my action is going to be the greedy action. So what I do is I look over all the QAs and I find the A that maximizes that. So this is the maximum value. Okay, or the action that gives me the maximum value. Then my reward is just, hey, whatever the bandits are, look at the bandit that is equal to that action. So if the second bandit gave me the highest value and I chose greedy action, then give me the second bandit and get a value from that. So however your bandits are set up, you know, if this is, like I said, if it's a slot machine, then just give me the random number from the slot machine. Then the other thing that I have to do is update the number of times that I've performed that action, right? So n action equals n action plus 1. And the very last thing I have to do is that update rule. Now, when I talked about the update rule mathematically, you have qk plus 1 was equal to qk dot dot dot. But when we actually implement this in code, you don't have access to qk and qk plus 1. It's all just values. So I'm going to say my value is equal to the previous value, and that'll take the old value, put it into the new value, right? So qa is going to be set to the old value plus, and this is the same as 1 over k plus 1, right? So this is 1 divided by na times the reward that we got minus the old value. So that's how we would implement incremental average with epsilon greedy bandit selection. And then over time, if you play this a few thousand times or whatever, hopefully by then you start pulling the right slot machine most of the time. Okay, so that's it's pretty intuitive, and that's reinforcement learning. It's pretty basic, but you are storing your values of actions and you're using those values to choose an action. Okay, that's it. This other formula, there are other ways to choose actions rather than just choosing randomly. And so exploration is needed because there's uncertainty, right, about the accuracy of your action value estimates. Greedy looks good right now, but it may not be the best. We do have to explore. And so we just, solved that problem with epsilon greedy, which explores, yeah, but it explores randomly, right? So for example, if you've got one action that's just always giving you miserable results, would you really want your random thing to keep hitting that one over and over? Maybe not, okay? So what UCB does, it's called upper confidence bound, it would be better to select among non-greedy actions that may be close to optimal with some measure about how certain we are about their values. And this is what the upper confidence bound method tries to do. Now this is horrible because my face on the video is going to be right in front of this. If I'm not lazy, maybe I'll edit it out. But this formula looks a bit intimidating at first, but essentially what it tries to do is this is the old value. Everything here under the square root, wherever you see a square root in statistics, usually this denotes some measure of variance or uncertainty, okay? And then C is going to be a constant that we multiply the uncertainty. So we've kind of got, here was our value, here's another number based on the uncertainty or variance of that value, add those together somehow, and now we have a balance between taking it based on its value and based on its uncertainty. So let's go look at each of these terms individually. So ln of t up here, that is the natural log of t. So that's because we don't want gigantic values underneath this square root. So we take the natural log, and this is the natural log of the total number of actions that we have performed. Underneath that is the number of times that a particular action was selected, okay? So let's say, for example, that t was 100, right? So if we've taken 100 total actions and we divide that by a high number, so let's say of the 100 total actions, we've tried this action 90 of those times, right? So as this number goes up, because it's in the denominator, our uncertainty goes down. So the more often we perform an action, this value is going to become less. And if we're choosing the maximum of these, then that means as I choose something more and more and more, this algorithm is going to choose to sample that one less and less and less, because it's the uncertain ones that I want to sample more and more. Okay, hopefully that makes a little bit of sense. Like, I've tried this one a bunch, therefore maybe I should try some other ones. Now, C is a constant that we are in control of. If I want to explore more, I bump up C, right? So if C was infinity, all I would be doing would be selecting the thing that I've chosen the least, right? And so that would be pure exploration. If C was 0, then I eliminate this term completely, and then what am I doing if C is 0? It's just greedy action selection. So this is balancing between exploration and exploitation, this formula. That's what it's trying to do. And so typically in UCB is what we do is we try everything once before we try anything twice. So there's one other step. We try everything once and then we start to implement this formula. So the square root term is the uncertainty value for the value estimates of action A. And the function calculates a sort of upper bound on the possible true value of action A. As NT of A increases, the uncertainty goes down. When T increases but not NT, the uncertainty goes up. And so what this has shown is that it can do better than epsilon greedy, especially if this is running for a long time. Okay? Because it sort of does that balance between exploration and exploitation on its own in that formula without having to do something like say, okay, I was at epsilon equal to 20%, now it's 5, and so it balances itself over time. Now, there are many, many other formulas for this, and all of those formulas, those are just different update formulas and action selection formulas that exist. I'm not going to get into all of them though. One thing that we will see going forward is that, so we've been talking about Q of A, right? But what we kind of really want is Q of SA, because Q of A is the value of doing action A. And if all I have in front of me are a bunch of slot machines, then I don't really have a state, right? There's just actions. There's only one state, and I'm just pulling these actions. But you can think if I actually have a real problem, then the value of actions is going to depend on the state in which I took that action. If I'm up in the very top right of a pathfinding environment, and there's nothing to my right, then the value of going to the right there is going to be very different than if I was just to the left of the goal. So it's not good enough to just talk about Q of A in the long run. We've got to talk about the value of doing actions at a state, not just the value of an action. So, just the example I just said, forgot I had it here, moving up is good if the goal is up, but it's not good if the goal is down. So you can't talk about just the value of moving up, because it depends on what state you're in for the value of moving up. So Q of SA is the value of doing action A at state S, or more accurately, it's our current estimate of doing that action. So here's the action that we have in our assignment of going up, down, left, and right. We can think of these as this is action 0, action 1, action 2, and action 3, and then these are the bandits. We don't know how good going up is at this state yet until we've tried it. We don't know how good going left is at this state until we've tried it. And so this is the value of QS up and QS down, QS left, and QS right. It depends on the state that you're in. Okay, so just keep this in mind. Basically, at any state that you are in, and it doesn't have to be just pathfinding, this is just the easiest two-dimensional example, but any problem you are doing, if it's blackjack, right? If I have these cards, what's the value of getting another card versus getting no more cards? Well, that depends on the cards that I already have, right? If I have 20, the value of hitting is way lower than if I have 11, right? If you know blackjack, you'll understand that, but really just driving it home here that the value of actions only makes sense when you talk about which state that you're in when you do that action. Yeah, and so possible exam questions. The first exam, the midterm, yes, there were some algorithms, but not many. If you thought about it in the first half, really we only did 2 algorithms. We did tree search and we did minimax. Everything else was just a slight variation to those 2. So the number of different calculation-based questions on an exam was very low. But now in the second half, where we're doing a lot of reinforcement learning, there is going to be a bunch of math algorithms that I could very easily put numerical examples on the exam. So anytime in any slide that I go through a mathematical example, it's very likely that that example will end up on an exam. I can't put all of them there, but like at least half of them will be on the final. So just know the formula for the average update, the average incremental update, be able to do the examples that I do in the slides, essentially. Exploitation versus exploration. be able to define those things, be able to give real-world examples of those things, be able to say, how does epsilon greedy help exploration versus exploitation? How does it help solve that problem? How does UCB do it? Action selection methods, greedy, epsilon greedy, UCB. If I ever do have a question about UCB, I will put the formula there. So I'm not going to get you to memorize that formula, but know what the terms mean. And I say something like, if I increase this value, what does that mean in terms of exploitation versus exploration? What is the value of, what is the effect of epsilon? If I gave you a graph and showed you 3 graphs, which one is probably epsilon equal to this versus epsilon equal to that? And just the Bandit algorithm in general, the pseudocode for that, and being able to write that down on the exam. Now, like I said, when I gave this Bandit algorithm here, so you have to choose a value update method and you have to choose an action selection method, right? I could ask you to implement this, but instead of incremental average, now it's fixed size alpha. Instead of epsilon greedy, now it's UCB, or it's greedy, right? So it's just one algorithm, but you have to choose how you're updating the values and how, and I will ask you that if I ask for that on an exam.